Analyze phase is the most important phase of a Lean Six Sigma project. The objective of Analyze phase is to identify all the root causes for Project Y. In the introduction module, we understood the expression of y is equal to function of x's. So, in Analyze phase, we will find out all the x's, the root causes for the y. Here is the approach to find out all the root causes. We analyze the data using graphical representations. The data gives us some root causes. We analyze the process using specific tools and techniques to get some more root causes. We analyze the inputs from people using brainstorming techniques to get the rest of the root causes. Finally, we consolidate and finalize the list of vital root causes using specific techniques. Since we analyze the inputs from data, process, and people, it becomes a very effective approach for root cause analysis. In short, we do a 360-degree analysis on the problem to find out all the root causes and to make sure that we do not miss any root cause. So far, we have covered the first two aspects of data analysis: how to collect various dimensions of data and how to represent the data using various graphical formats such as bar chart, pie chart, histogram, scatter chart, and Pareto chart. Now we will see the last aspect of data analysis. Let us look at another example. Let's say our project Y is reduce delays in data warehouse projects. While collecting various dimensions of data, we collected the data of number of delayed projects per each type of project. And the data is graphically represented using pie chart. Now, we need to analyze this data and explore the root causes for the project delays. For example, this data shows that the delays are more for Type 1, Type 3, and Type 5 projects. 35% of Type 3 projects are delayed. 23% of Type 1 projects are delayed. Now, we need to probe further on why there are more delays for these projects. When we probe further, we may find out multiple root causes. For example, poor understanding of requirements causing rework and delays. Improper estimation of project schedules during the initial stages of projects. Project managers of these types of projects were not trained well, and so on. So, from data analysis, we found these root causes for the delays in telecom projects. Now, let us understand the details of special causes and common causes, and their relevance to data analysis. Let's understand with this example. For example, our project Y is reduce turnaround time to process vendor payments. And here is the data of turnaround time to process vendor payments. If we analyze this data, the turnaround time for all the vendors except vendor 8 is under 20 days. The turnaround time for vendor 8 is 132 days. Let's say the higher turnaround time for vendor 8 is due to a legal dispute. This is called a special cause, which causes an abnormal variation in data. The variation levels in the rest of the data appears to be normal. In other words, the variation is not abnormal. And the causes for these normal levels of variation are called common causes. Please note, we should not include the data of special causes when we measure the current performance in terms of z-score and when we do the data analysis. If we include them, the performance measurement value will be a distorted one. Special causes are also called assignable causes because we can clearly assign a cause for the variation. Common causes are called chance or random causes. Special causes are easy to identify, whereas the common causes are not so easy to identify. Special causes incur significant impact. whereas the common causes incur small impact. However, they collectively cause bigger impact on Project Y. Special causes are typically not in our control. The common causes are typically in our control. Special causes occur less frequently. In other words, they are sporadic, whereas the common causes occur more frequently. In other words, there will be more common causes than special causes for a Project Y. So, the collective impact of common causes would be significant. Please note, the aim of Lean Six Sigma is to reduce or eliminate common causes because they are in our control.
We have seen in the measure phase that statistics has two branches: descriptive statistics and inferential statistics. We have covered the descriptive statistics in measure phase. Now, we will learn about the inferential statistics. Inferential statistics is the process of making inferences about a population based on a sample through specific techniques such as estimation and hypothesis testing. Please note, you may use your discretion while applying these advanced statistical concepts since they depend on highly accurate and reliable data. Let us look at the procedure to estimate the population mean. If the mean and standard deviation of a sample are known, we can estimate the mean of the population using z-statistic or t-statistic. If the sample size n is greater than or equal to 30, we use z-statistic approach to estimate the population mean. If the sample size n is less than 30, we use t-statistic approach to estimate the population mean. It is a standard practice to estimate the population mean with a confidence percentage and within a range of values. This range of values is called the confidence interval. For example, we estimate with 95% confidence. In other words, we estimate with 0.95 probability that the population mean lies in between the confidence interval of 25.5 and 31.3. Hypothesis testing is a well-defined procedure to decide whether to accept or reject a hypothesis made on a population parameter based on a sample statistic. Please note, depending on the context, hypothesis testing can be done in analyze, improve, or control phases of a Lean Six Sigma project. You may use your discretion while applying these advanced statistical concepts since they depend on highly accurate and reliable data. Let us have a look at the hypothesis testing procedure. The first step in hypothesis testing is to set the null hypothesis. The null hypothesis is denoted by HO. Then we set the alternate hypothesis. The alternate hypothesis is denoted by H1. There are three choices for alternate hypothesis: a two-tailed test, a left-tailed test, and a right-tailed test. We choose any one of these alternates according to the given context. Then we obtain the level of significance alpha. Alpha is equal to 1 minus the probability value of the confidence level. For example, for a confidence level of 95%, the alpha value is 0.05. We have already covered the concept of alpha in detail. Then we compute the sample statistic value, such as z-value or t-value, etc. If the computed value is within the acceptance or confidence region, we accept the null hypothesis. Otherwise, we accept the alternate hypothesis. This is the procedure to do the hypothesis testing. We will understand this procedure and the terminology clearly when we look at the examples and exercises. There are various hypothesis tests available for continuous data and for discrete data. We will cover these hypothesis tests one by one. Now, let us look at the first test, one sample z-test.
Let us understand the procedure to do this hypothesis test 1 sample z-test for population mean. The first step is to set the null hypothesis. The null hypothesis is expressed as follows. HO is mu is equal to mu naught. Let's understand this with an example. Let's say last year's mean payroll accuracy is 85%. So, the null hypothesis statement for this example is this. HO is mu is equal to 85, which means we are proposing the null hypothesis as the current year's mean, mu, is the same as last year's mean, mu naught, which is 85. In other words, we say there is no change in the mean value. The next step is to set the alternative hypothesis. As we have mentioned earlier, there are 3 choices. In other words, 3 possible alternative hypothesis scenarios. Here is the choice 1, or the first alternative hypothesis. It is stated as follows. H1 is mu is not equal to mu naught. This is called a two-tailed test. When we apply this statement to the given example, the alternate hypothesis statement is as follows. H1 is mu is not equal to 85, which means we are proposing the alternate hypothesis as the current year's mean mu is not the same as the last year's mean mu naught, which is 85. In other words, this year's mean may be less than 85 or more than 85, but not equal to 85. Here is the second choice, or the second alternate hypothesis. It is stated as follows. H1 is mu is less than mu naught. This is called a left-tailed test. For example, last year's mean payroll accuracy is 85%, and the mean value of this year's sample is 79%. So, for this example, the alternate hypothesis statement is as follows. H1 is mu is less than 85, which means we are proposing the alternate hypothesis as the current year's mean mu is less than last year's mean mu naught, which is 85. Here is the third choice, or the third alternate hypothesis. It is stated as follows. H1 is mu is greater than mu naught. This is called a right-tailed test. For example, last year's mean payroll accuracy is 85%, and the mean value of this year's sample is 92%. So, for this example, the alternate hypothesis statement is as follows. H1 is mu is greater than 85, which means we are proposing the alternate hypothesis as the current year's mean mu is greater than last year's mean mu naught, which is 85. So, according to the given data, we choose one suitable alternate hypothesis. We will now see how to do the hypothesis testing for each alternate hypothesis scenario.
Now, let us understand with an example on how to do a right-tailed test of one sample z-test. Here is the example. In an organization, the last year's mean payroll accuracy was 85%. This year's sample shows the mean payroll accuracy is 92%, and the standard deviation is 7.75. The sample size is 40. Using hypothesis testing, verify with 95% confidence level whether the mean payroll accuracy is increased from previous year's value. From this data, we can confirm the value of mu naught as 85, which is the last year's mean. X bar is 92, which is the current sample's mean. S is 7.75, which is the standard deviation of sample. The sample size N is 40. And for a confidence level of 95%, the value of alpha is 5%, which is 0.05. Step 1. Set the null and alternate hypothesis. As we understood earlier, the null hypothesis always says there is no change, so HO is mu is equal to 85. Now, to set the alternate hypothesis correctly, we need to clearly understand what the question is. Here we are asked clearly to verify whether the mean payroll accuracy is increased from previous year's value. So the alternate hypothesis H1 is mu is greater than 85. When we set the H1 as mu is greater than mu naught, it is called a right-tailed test. Step 2. Calculate the right side Z alpha value using Norm's INV function in MS Excel. Alpha is 0.05. The left side Z alpha value is Norm's INV of 0.05, which is equal to minus 1.645. So the right side Z alpha value is plus 1.645. The Z alpha value is also called the Z critical value. Step 3. Calculate the Z computed value using the formula. Here is the formula to calculate the Z computed value. Using this formula, we get the Z computed value as 5.71. We have set the null and alternate hypothesis. We have got the Z computed and the Z critical values. Step 4, the last step. If the Z computed value is less than the right side Z alpha value of 1.645, accept the null hypothesis. Otherwise, accept the alternate hypothesis. In other words, if the Z computed value is greater than 1.645, we reject the null hypothesis and accept the alternate hypothesis. For this example, the Z computed value of 5.71 is greater than 1.645, so we reject the null hypothesis and accept the alternate hypothesis H1. Mu is greater than 85. Hence, with 95% confidence level, we say that the mean payroll accuracy is increased from previous year's mean value. These are the steps that need to be followed to do the right-tailed hypothesis testing for one sample Z-test. Let us understand the right-tailed test with graphical illustration. This is the Z-critical value, Z-alpha. In other words, 1.645. The 95% confidence region or 0.95 probability area under the curve is the acceptance region for null hypothesis. The alpha or 0.05 probability area on the right side of the curve is the rejection region. If the Z computed value falls in this rejection region, we reject the null hypothesis. If the Z computed value falls within the acceptance region, which is less than 1.645, we accept the null hypothesis. For this example, the Z computed value is 5.71, which clearly falls in the rejection region. So we reject the null hypothesis and accept the alternate hypothesis H1. Mu is greater than 85. To help you do the one sample Z-test easily, Edushore has developed a calculator template. Here is the file name of one sample Z-test calculator template that is provided to you. All you need to do is just enter the known values of mu naught, x bar, sigma or s, sample size n, and the confidence level. This calculator generates all the rest of the values for you, such as the Z computed value, Z critical values for two-tailed, left-tailed, and the right-tailed tests. It also provides you the guidelines to interpret the results so that you can arrive at the right conclusions. Please note, any kind of Z-test should only be used when the sample size is greater than or equal to 30.
We have covered all the hypothesis tests for continuous data. Now, we will look at the first hypothesis test for discrete data, chi-square goodness of fit test. Let us understand the characteristics of chi-square distribution. Chi-square is denoted by this symbol. The chi-square value is always positive. The chi-square distribution is skewed to the right. Here are the assumptions for chi-square distribution. The expected frequency of a cell must be at least 5. The sample should consist of at least 50 random observations. Data should not be in percentage or ratio form. Data should be expressed in original units. Here is the formula for chi-square value. Let us understand the chi-square goodness of fit test. Here is the procedure to do chi-square goodness of fit test. The null hypothesis, HO, says the data points are uniformly distributed. The alternate hypothesis says the data points are not uniformly distributed. For the given values of alpha and degrees of freedom, obtain the chi-square critical value by using the chi-inv function in MS Excel. Calculate the expected frequency value for the given data. Calculate the chi-square computed value by using the formula or by using chi-test and chi-inv functions in MS Excel. If the chi-square computed value is less than the chi-square critical value, accept the null hypothesis. Otherwise, reject the null hypothesis and accept the alternate hypothesis. We will understand this procedure more clearly when we do an exercise. The objective of Analyze phase is to find out all the root causes for the project Y. We do a 360-degree analysis which consists of analyzing the data, analyzing the process, and analyzing the inputs from people. In the previous sessions, we have seen how to do the data analysis and how to do the process analysis to get the root causes. Now, we will look into the aspects of analyzing the inputs from people. We have seen that the data gives us some root causes, the process gives us some more root causes, and we get the rest of the root causes for the project Y from people through brainstorming. Let us look at the guidelines for effective brainstorming. The first and the foremost, we need to be very clear on the purpose of the brainstorming in Analyze phase of a Lean Six Sigma project. The purpose of brainstorming is to find the root causes for the given project Y. For example, our project Y is reduce the cycle time of testing. So, the focus of our brainstorming discussions with the people should be to get their inputs on why the cycle time of testing is currently high.
We should involve all key stakeholders of the given process in the brainstorming meetings. They include the internal as well as the external stakeholders. If we miss out any key stakeholder, we may be missing some significant root causes for the project Y. In some cases, we may not be comfortable with customers' presence in the brainstorming meetings. In such cases, it is better to collect their inputs through other means, such as by sending a questionnaire through email, getting their inputs through a phone call, etc. It is better to limit the size of the brainstorming team to a maximum of 10. There are some studies done that suggest if the size is going beyond 10 people, there would be challenges to manage the communication channels among people. It is better not to disclose the findings of data analysis and process analysis in the beginning of brainstorming meeting. This will bring out fresh views from people on the root causes for Project Y. And they will not be influenced by the earlier findings. However, findings of data and process analysis may be shared at a later stage during the brainstorming meeting. We should make the discussion environment cordial. One member may be nominated as a facilitator to make the discussion unbiased, organized, and time-bound. We should let every member speak and express his or her viewpoint freely, and we should not reject any viewpoint in this meeting. In these brainstorming meetings, we should focus on finding the root causes for the stated problem of our project Y only. We should avoid getting digressed into discussions on some other problem. And we should focus on finding the root causes only, not the solutions. We should avoid getting indulged into discussions on solutions. Please remember, the objective of Analyze phase is to find the root causes, not the solutions. All these guidelines make the brainstorming very effective. They help us find a rich set of root causes from people.
So far, we have seen various techniques of doing a 360-degree analysis on Project Y. When we analyze the data through various graphical representations, we get some root causes. When we analyze the process by using techniques such as value stream mapping and FMEA, we get some more root causes. And when we analyze the inputs from people through brainstorming, we get the rest of the root causes.